Swayam Prabha. Digital India. Educated India.
Good afternoon. What we are going to talk about today is primarily about generalized elements. And in the previous lecture, I had laid out some context as to why we would need these generalized elements. Since I have not talked and provided much detail about this whole idea of generalized elements, you may not know much about it. But as we go further in the lecture, you will see what a generalized element is and why it is needed. So primarily, the logic behind developing this theory or these equivalences is that, for instance, in a sound device such as a loudspeaker, you have electrical energy coming in, it gets converted into motion or mechanical energy. So you have first transformation of energy, then you have another transformation where that motion gets converted into sound. And to bridge the domain of electrical engineering, the domain of mechanical engineering where you are dealing with motion, stresses and strains, and the domain of acoustics, you need some mechanism or theory. And if we use lumped parameter approaches, which work fairly well for devices such as loudspeakers, microphones, and a bunch of other acoustic devices, then this generalized element approach comes in very handy. So we talked about loudspeakers. Now let's look at microphones. So in general, a microphone is a device where you have sound which is being sensed as pressure, and then it gets converted into electrical energy. We have 5-6 major categories of microphones. So the first one is a condenser microphone. And what you have there is that you have a membrane which senses pressure, and then as that membrane moves back and forth, it causes the motion of a plate which is also moving with it. In some cases, the membrane itself could be a metallic plate. So you have one membrane moving back and forth, and then the other plate is fixed. So this membrane is moving back and forth. So the capacitance between the two plates changes, and it responds to changes in pressure fluctuation caused by sound disturbances. So you sense that change in capacitance, and then you convert it into acoustic pressure through, again, some equivalences. Then another type of a microphone is a dynamic microphone, and there it's essentially an inverse of a regular loudspeaker. So what you have in a dynamic microphone is a membrane which senses pressure, because because of that pressure fluctuation, it moves back and forth, which in turn gets converted into electrical energy, either voltage or current, and then that voltage or current is measured, and then it gets translated back by some equivalence relations into SPL, sound pressure level. Then there are piezoelectric microphones, where you have the conversion process as sound. Sound causes a piezoelectric crystal to experience some pressure, and when that pressure grows up or it goes down, that generates voltage in the piezoelectric crystal. So again, you have a transformation of energy, sound to pressure to electricity. There's another device, a microphone device, fiber optic microphone. So what you have in fiber optic microphone is, again, you have a membrane which is moving back and forth. One side of that membrane could be polished, and it could be a reflective surface. So light from some other place comes and it gets reflected, and as this membrane is moving back and forth, the intensity of that light gets modulated. So then there's another sensing device which senses the change in light intensity, and that change in light intensity is then interpreted back into sound pressure level. So in all these measuring equipment, different types of measuring equipments, you have transduction happening. So there is a need to have some sort of theory on an approach through which you can bridge the gap between electrical, mechanical, sound, or electrical, optics, sound, or electrical, piezoelectric mechanics, sound, and so on and so forth. So what we will cover today is essentially we'll develop few types of generalized elements, and then we will see how they map into electrical and mechanical domains. So that will be the focus. So I can have a generalized element and I can symbolize it something like this. It could be a positive here, a negative here, and it could have three variables. So the first variable, let's call it A. The second variable, let's call it B. And the third variable, let's call it C. And what we say is A is an across variable. For instance, in a resistor, what is across the voltage? So voltage could be an across variable. B is a through variable. It's flowing through the element. And C, we call it the element variable. And it's essentially a property of that generalized element. So again, if we have a resistor, through variable could be current, as current is passing through it. And a cross variable could be voltage. And the element variable could be the resistance itself. It's a property of that device. Right? And this is all for linear theories. These elements, as we are developing, we will be using in context of linear systems. So what we will develop is, we'll develop four types of elements. The first type will be two-terminal. Two-terminal element. The second element which we will talk about is a four-terminal element. The third element we'll talk about will be source, and this will be, let's say, type A. And the fourth element we'll talk about is again a source, and it will be type B, or you can call it type 1 or type 2. So we'll start with two-terminal elements. So the first two-terminal element has a relationship where A, which is the across variable, is through variable times element variable. Any element which has these three variables linked in such a way is a two-terminal element of this particular type. So for instance, you have a resistance, there is a voltage across it, and there is current going through it. So in this case, my A is voltage, B is current, and C is resistance. Okay. We can also say that B equals 1 over C dot A. So these are the two forms of a two-terminal element, and there are different categories of two-terminal elements. So this is first type. Let's look at another two-terminal element. So in this case, the across variable A is equal to time derivative of B times C, or B equals A over C dt if I integrate it. So again, if I map it to electrical domain, this looks like an inductor. So again, my through variable is voltage, current. Through variable is current, across variable is voltage, and the element variable is L, or the inductance. So this is another form, a two-terminal element, and it's called a two-terminal element because it has two physical terminals. Similarly, an inductor has two physical terminals. Do the third type of this two-terminal element, and as you would expect, it would look something similar to a capacitor. So here, the through variable, which is B, equals 1 over C times time derivative of A. So you have a capacitor, there's current going through it, and there's voltage, and voltage and current are related in such a way as defined by this relation. And I can also reformulate this relation such that A equals B times C dt when I integrate it. So this is the third category of a two-terminal element. We have talked about two-terminal element. Now let's look at a four-terminal element, which is another thing we talked about. So what we are going to four-terminal element. So can you guys guess a four-terminal physical device which has four nodes? Transformer. Exactly. So what you have is, these are two terminals, and then the other two terminals are here. This is one across variable, another across variable is G. Then there's a through variable B, another through variable is H, and the element variable is another number we call T. So T in this case is turn ratio. And what we have drawn is essentially an ideal transformer. So in this case, the relationship between A and G is A equals T times G, B equals 1 over T times H, and then we also know that AB equals GH. Okay? So we are right now talking only about electrical side of things, but we will see how these ideas also translate into the mechanical world. So this is a four-terminal element because it has 1, 2, 3, and 4 terminals. So the third category of terminals was source, type A. And here what it is so essentially what we are saying is that the element variable C is same as A, and this is the case for an ideal voltage source. as an example. That is, its internal resistance is virtually 0. No, I think I wrote it incorrectly. Yeah, because there's an arrow here. So this should be, and this should be an ideal current source. And the fourth one is source type B. It should be B. See, so what you have here is a source with an element value of C, and the through variable is B, across variable is A. Then in this case you have C equals A, and an example would be ideal voltage source. Okay.
In the first case, I think it should be B equals A.
B equals
C.
C, which is what is there. Okay. So again, we talked about different generalized elements, and now we'll just formally, even though we know in electrical engineering which is what, we'll just formally document. So in electrical engineering, if I have a resistance, current, and then there's voltage across it, then A equals B dot C maps to V equals I dot R. If I have an inductor with an inductance L, current is I, voltage across the inductor is V, then A equals dB over dt times C. This relation maps to voltage equals L times rate of change of current. If I have a capacitor seeing a current I, again voltage across it being V, then A equals integral of B dot C dot dt. This relation maps to voltage equals I times 1 over capacitance times dt. And then I integrate it. And my 4-point element, my input current is I1, voltage across is V1, and then output voltage is V2, current is I2, and turn ratio is T. Then the relationships are V1 I1 equals V2 I2, V1 equals this turn ratio times V2, and I1 equals 1 over T times I2. And then finally I'll formally list the two sources. So I have a current source, current, internal current, which is the element variable is I, and the current going through the circuit is lowercase I, voltage across the source is V, then here I equals I. And similarly, if I have a voltage source, then my relationship will be equals V. So till so far it is all standard, but just to provide a context, I have a generalized element and I am mapping that generalized element into electrical engineering. So as the next step, what I will do is map it into mechanical area. So what we will find is that if I use a specific type of analogy, then we will see that the through variable turns out to be force, and we'll see it, how it comes out. And the cross variable in mechanical world comes out as velocity. So force is analogous to current, it's a through variable, and velocity is analogous to voltage. So we'll see. So the first element was A equals B dot C, which is a resistance. So what is a resistance in mechanical land? It's a dashpot. It's dissipating energy. So let's look at it. You have a dashpot. The cross variable is U. The through variable is force. So U equals force times mechanical resistance, or force equals 1 over Rm times U. Yeah. So in laws of mechanics, through you have seen that F equals Cx dot. This is your x dot, U, and C is 1 over Rm, right? So we have seen this equation.
So then how force is through variable? Why through variable?
Because force is felt throughout the line, flow line. So this equivalence is preserved in a spring and in a mass. You will see it. So it just happens that our traditional damping coefficient, which we use as C, we will not use C as damping coefficient in context of acoustics as it is being taught in this particular course. So if C is damping coefficient, such that force equals Cx dot equals Cu, then damping coefficient is essentially 1 over Rm, and I call this Rm as mechanical resistance. What is the unit of Rm? It will be inverse of unit of damping coefficient. So that unit is meters per second newtons, right? So as you are doing your calculations using this approach, you should make sure that you don't equate C with Rm. There's an inverse relationship. That is a mistake which happens very often. So we talked about mechanical resistance or a dashpot. So the second two terminal element is a spring. It just happens that the symbol is very similar. So my through variable is F, my cross variable is U, and we know that force equals stiffness times displacement. So if I differentiate it, I get this relation, K times U. Okay, so if I rearrange, I get U equals 1 over K times time derivative of force, or I can say, if I have to find force, is basically, so we'll go to that later, but 1 over K, we term it as Cm, or compliance. So again, this relation looks very similar if I write this U equals Cm times df over dt. this relation looks very similar to voltage equals di over dt times L. So I am seeing again the same equivalence is being preserved. It is being preserved in the case of a mechanical resistance. Here I, you have a derivative of I, you have a derivative of F. You know, voltage, you have velocity. So that relationship is being preserved. So this is called compliance, or it is also called mechanical inductance. And most of the people use the term compliance. But you should know, if someone uses mechanical inductance, you know, CM. So resistance, we saw that in case of a resistance, the relationships are preserved. U being equal to voltage, equivalent to voltage, current being mapped into force, and the element variables. So now let's look at mass. That's the third variable. So we know that force for a mass which is accelerating is mn times acceleration, which is a time derivative of velocity. And I can rearrange it. So I get u equals 1 over mm times f dt if I integrate it. So again, this is again looking similar to the relation as you have in a capacitor. So the equivalences are preserved amongst spring is similar to an inductor, mass is similar to a capacitor, and a dashpot is similar to a resistor. And how do I depict it? So this is my mass. I have a through variable f, and the cross variable is u, which is velocity. This is the inertial frame. This thing is your inertial frame. So this is one difference, because whenever we measure acceleration, we measure it with respect to an inertial frame. So I have drawn an inertial frame here. So whenever you have a mass in a system, when you try to convert it into a, you know, a capacitive, something similar to a capacitor, you have to make sure that you refer to, you always have provide with a reference frame in an inertial frame. This is important. So we did what? So is that clear? How the analogy between force, velocity, and current and voltage work, and also how mass gets translated into a capacitor, a spring gets translated into an inductor, and a dashpot gets translated into a resistance. What could be a 4-node or a 4-terminal element in mechanical area? Think about it. You have a transformer in electrical. What could be a 4-node element?
Gears.
Gear is one, yeah, very nice. Yeah, gear is one. Yeah. Gears or levers. You know, you have a lever, you have F1, V1, you know, force and velocity on one side, it gets translated into force and velocity on the other side. And it's essentially the same ratio of length, the two lengths. So that is what we'll talk about. And you can just map the same thing for gears also. So a 4-terminal element. And so I have a lever, and I can do the same thing for gear. I have a fulcrum. I have two input variables, F1, U1, F2, U2. Then the relationships are U1 over L1 equals U2 over L2, F1 L1 equals F2 L2, and this is analogous to a transformer. So here it will be U1 plus minus, this is the through variable, this is the second through variable U2, and this is my turn ratio. This is the ratio of the lengths I can put. And similarly, we have a current source and a voltage source in electrical land. We can similarly have a force source and a velocity source in mechanical land. What is a force source? If you have, there are some machines, tensile testing machines. You can either have a force controlled experiment, or you can have a displacement or a velocity controlled experiment. So when you are having a velocity controlled experiment, essentially you are having a velocity source in the system. If you have a force controlled experiment, then you have a force source in the system. So these equivalences are preserved. Transducer, most of the transducers, they control the velocity, and the force is as an output of external conditions and the overall impedance outside it. But the transducer knows how much to move back and forth. So if it knows how much to move back and forth, then it's a velocity controller. So you have a velocity source. Now there are, other types of transducers also. So you have to know which type of sources you are placing in the system. Okay. So we have seen different types of equivalences between mechanical elements and electrical elements. So we should also see one more special thing about transformer, which could be a gear or an electrical transformer or a lever, that it is possible, if you have drawn a circuit, to eliminate the transformer at all by appropriately changing the values of some inductances. So that is what we will see. So you have a transformer, let's say its turn ratio is T is to 1. Again, these are my 1, 1, 2, I2. So, and this is connected to an external impedance, which is Z. Okay. So we know that Z equals V2 over I2. So Z equals V1 over T over I1 times T, right, equals V1 over I1. And bear in mind, when I am writing V and I, actually I should have been a little bit more careful. These should be in uppercase because these are vectors, because there may be a phase component in Z. So V1 over I1 times 1 over T square. Now what this means is that I can replace this entire box by another box, which will be something like this. Right? Is that clear? So whenever you have a transformer, or whenever there is a transformation happening, this is important to understand. Whenever there is a transformation happening from electrical to mechanical, and if you can figure out what is that ratio, for instance, in a coil which moves back and forth, force equals BIL, right, from laws of electromechanics. So the turn ratio there is BL, because force equals BIL. So then you can have a mechanical circuit, you can also have an electrical circuit, and they are initially broken because of the transformer, but you can remove that transformer and combine the electrical and mechanical circuit into one single circuit, and you can change the impedance on the mechanical side by using this factor, right? So we'll do some couple of examples and how these transformations happen. So in case of a resistor, and we will do more as we draw complete circuits of loudspeakers and microphones. So you have V1 and I have a resistance R, and my turn ratio is T:1, I1, I2. So this is equivalent to T square R. So I can eliminate the transformer and I can just replace it by an increased resistive load or change resistive load, change by a factor of T square. So the other one is an inductor, and in this case I have L as the impedance. So this transforms to L times T square. And the last one is of a capacitor. Yeah. So I have a capacitance C. This transforms to C over T square, because your impedance is inverse of C. So again, some of these concepts are drawn from electrical engineering, but you will find them extremely useful as we try to solve acoustic problems and so mechanical problems. We will do one more example and see how it changes. So if my circuit is like this, and the turn ratio is T:1, if let's say it's an RLC circuit, RLC, then this is changing to my resistance value changes to R T square, L goes to L T square, and capacitance changes to C over T square. So it does not matter. You can solve this circuit or you can solve this circuit. The answers will be same. So depending on the situation, you can figure out, do I want to solve this circuit or do I want to solve this circuit? Whichever appears easier, you can use that. So we have talked about how resistances, inductors, capacitors transform into mechanical equivalents and back and forth. How transformers can be changed back and forth, and also how sources in electrical area map into mechanical area and vice versa. As we are doing this analysis in circuit analysis for electrical engineering, if it's a complex circuit, then we use two laws to solve for different currents and voltage. One is the Kirchhoff's current law and the other one is Kirchhoff's voltage law. So you can again, we'll need similar laws for mechanics area to solve electromechanical problems. So we have a Kirchhoff's current law where through a node, if I have I3, I1, I2, then the Kirchhoff's current law says that through a node I equals 0. That is I1 plus I2 plus I3 equals 0. And this maps if I have a node, a current node for in the mechanical area, what this also translates to is F1 plus F2 plus F3 equals 0. And this is essentially your Newton's motion law of motion. So Kirchhoff's law is similar to Newton's law. They are not same, but they are similar. Similarly, you have Kirchhoff's voltage law, that if you have three elements, and a closed circuit, and the voltage across third element is V3 minus plus, here you have V1 plus minus, and here you have V2 plus minus, then KVL says V1 plus V2 plus V3 equals 0. And this comes from law of conservation of energy. There's an assumption here that there's no external flux, but we don't have those conditions, then this holds good. In mechanical land, this translates to U1 plus U2 plus U3 equals 0. And that is basically your law of conservation of mass, continuity. Right. So these are important rules to remember as you are trying to do an electromechanical circuit analysis. So we'll do one or two very quick examples and see how we can use some of these techniques. So let's say I have a very simple spring mass system. So the mass is mm. The spring has a stiffness of K, which is or a compliance of Cm, and it's being excited by some source velocity. So let's say if I am interested to find what is velocity of the mass. I want to know what is the velocity of mass. In other words, I want to find, if I map it to electrical world, what is the potential difference across the mass, right? Because velocity is mapping to voltage. So I make a circuit out of it. So Us is like a voltage source. What is going through the circuit? Force is flowing through the circuit. And then I have a spring or an inductor of inductance Cm. And then I have a mass. Which is grounded. So I can now convert it into formally electrical circuit. So I have a Us, my I equals force, Us is velocity source, velocity. I know this, and I can put a capacitance here, and again, because capacitance is grounded, that condition is being satisfied, and this value of capacitance is mm. Okay, so my total impedance in the circuit Z equals I equals mm dV over dt. You should set them in the equation. It will be mm. So Z equals SL, S is j omega plus 1 over S m m equals S square L m m plus 1 over S mass. So I put S as j omega, so what I get is 1 minus omega square L m m over j omega m m. Is that right? Yeah. So now I want to find the velocity of this mass or the voltage difference across this capacitor. So I can find the current, I multiply by the impedance offered by mm. So the force, which is same as current, when I map it, is Us over Z, and that comes to be j omega mm over 1 minus omega square L mm times us. So my velocity across the mass is, this is current, force, right? This is equivalent to current. So is force times impedance of the capacitor. So 1 over omega c j. So this gives me qs over 1 minus omega square L m n. So instead of doing a lot of force equilibrium and solving differential equations, I am relatively easily able to solve for the velocity of moving mass by using some concepts of circuit analysis. Right. So that is the whole point. Let's do one more example. So now you have a spring of compliance Cm, a dashpot, and both these springs and the dashpot are connected to mass, a moving mass mm. The damping coefficient is C, which is inverse of mechanical resistance. We talked about it. So if you know the damping coefficient, you should be able to figure out what is Rm. And I am at this point, I am exciting it with a known velocity. So it is source velocity. So then the question is, find the velocity of this moving mass. So what is this value? That is the question. So first I draw a circuit, and what I get is so again I have US here, which translates into a voltage source of strength US. Current is F, and then I have an inductor, I have a resistance, and then I have a capacitance. The value of capacitance is same as the mass of the object. Value of inductance is Cm, and this value is 1 over Rm. So my overall impedance across these 2 points is 1 over S times moving mass, which is because of the capacitance, and then for the inductance and the resistance I get Rm plus 1 over S times inductance, which is Cm, and then I take inverse of that. So I can
Resistance will be Rm. Resistance should be Rm, not 1 by R.
I have to take inverse of it. This resistance and this inductance is in
Resistance will be
parallel.
Rm, that is 1 by C.
In next question you have written okay.
Yes, I'm sorry. This should be Rm. Yes. So here I should make it 1 over Rm. Okay. So through this I can figure out what is the value of Z. Using that Z, I can figure out that F equals US over Z. So I know the current flowing through the capacitor or the force seen by the mass, and then from here I can evaluate what is the value of velocity. So which is, so U m equals 1 over S mm times force. Relatively simpler or a straightforward process. So in this whole exercise, what we have done today is establish couple of equivalents, not couple, several equivalents between an equivalence between resistance and a dashpot, a spring and an inductor, and between mass and a capacitor. And then force translates to or becomes equivalent to current, and velocity transforms to voltage. This is one way of establishing the equivalences. Now, if you play with the variables in a slightly different way, you can establish equivalences which are just the opposite. So resistance will still map into a dashpot because it's dissipating energy. But a spring can map into, here we saw that the spring is mapping into an inductor, but you will be able to map a spring into a capacitor. So either you use those set of principles or you use this set of principles which we spoke today, you will get the same answers. But you have to be, as we are doing this mapping exercise, we have to be sure that we are consistent. So there are people who will do the same sort of analysis, but in their calculations, force will translate into voltage, and velocity will translate into current. And in that particular scenario, spring maps into a capacitor and so on and so forth. So there are two different, very similar but still different approaches of doing these, conducting these transformations. But at the end of the day, what we have shown today is that we can bridge the gap between electrical engineering and mechanical engineering, and we can create one single large circuit where electrical energy is coming in, and as an output what you are having is motion being exhibited by the mass. So if you have a transducer or a speaker which is moving back and forth, and if you want to know that if I am putting in 100 watts of energy at 20 hertz, how much this diaphragm is going to move, I should be able to calculate using this approach. Now I still have not bridged the gap between motion and sound. We have not talked about sound at all today. But in some of the subsequent lectures, we will speak about how that motion gets transformed into sound based on some of the transmission line theories we studied earlier, 1D wave equation, and so on and so forth. But through this way, we have an approach how we can bridge the realm of electrical engineering, mechanical, and acoustics. And in case of a lot of electromechanical acoustic systems like speakers, microphones, sensors, this approach works fairly well because most of the elements are very close to lumped parameters. So 1D approaches and lumped parameter approaches work very well in a lot of applications. So it's really worthwhile understanding it. The other thing is that once you have created an elaborate circuit, you may find that it has 5 or 6 resistances, 6 or 7 capacitances, several inductors. How do you solve that? So one approach could be that you go through, do it through the hard way and solve and take a lot of time. But there are standard software packages in electrical engineering. One package is a PSpice. So you take and it has graphic tools. So you pull a resistance, put it on the screen, connect it to a capacitor, connect it to a resistance, connect it to another capacitor or an inductor, the way you have constructed the overall circuit, excite it through a voltage, and you will get an output number. So all that can be automated, but we have to know how to construct those circuits. So what we are learning is how to construct those circuits, and then at some point of time we will see how we can use some of these standard tools. We dump all those circuits into those software tools and then solve for whatever variables you want to know. So that is what I wanted to talk to you all today. and in the next lecture we'll further develop some of this stuff which we have been talking about.